We are PolyN, the new Neuromorphic company. We did solution for sensor-specific chip because it's important to provide ultra-low power, low latency solution for many products and everywhere where you need embedded system running neural net model.
Welcome, IPXers. As you know, world famous IPX studio with the big pink X. We love disruptive technology. Whole point of this channel, whole point of our content is to find disruptive companies that you may not have heard of. And I haven't used this phrase for a while recently, alien technology. I love interviewing people, chatting to people about things where you think, no, that can't be right. That doesn't make any sense. We found one, PolyN. And Alexander, who is on this call with me, he's going to be telling us all about neuromorphic processing and why it's called PolyN and where the N comes from. And then he's going to introduce us to his technology. So, Alexander, tell us all about PolyN, what the N stands for.
Yes, so thank you. Thank you for a chance to explain our story and technology. And PolyN, it's 5 years ago, born from idea of few mathematicians. He came to me with idea how to transfer mathematical model, so mathematical neural net model, to structure, physical structure. And that is important because now we not use full benefits of neuromorphic computing. Why not use? Because we use neural net model, which is very efficient for some data processing. For example, you can chat with neural model, but we still use this model as a digital system. It means we calculate step by step. So we still have cycle as any digital system. It's maybe gigahertz, it's a billion cycle per second, but anyway, it's a cycle. You step by step modeling. And the idea of my co-founders was we can use digital system and classical framework for model training, which is now works fine, and then convert when model is done, when it's trained and performed well, and you can verify, you can test, and when it's finalized, we can convert this to real parallel structure where neurons work like in our brain in parallel, in simultaneously.
Yeah.
And that promise unprecedented gap of power efficiency because you work in through parallel process and latency. And today it's vice versa. If you need low latency, you compromise its power. So you need higher frequency of your processor. It means your power consumption is higher. It's no magic. Higher performance, higher power consumption. We can solve the problem. We can have in the same time ultra low latency and ultra low power in our structure. That is the initial concept. One was generated 5 years ago. And why PolyN? Because initially we think to use polymer memristors for this structure. And when we launched the company, our idea was to use polymeric structure. But after a few months of research, we understand that it's not working. We use more standard CMOS technology, but company is already registered and nobody changed the name, and so we still have PolyN.
What technology is the PolyN solution replacing, or what would a design engineer have today that you're saying, okay, if we look at this problem a different way, this is how our product, our technology comes into play? Maybe you could answer that question for us.
Yes. So I try to answer. First of all, we are not replaced. I think we open new opportunity for new product, and that is not in segment of high performance computation. So we are not about cloud-based system. That is absolutely another segment. But if you work in embedding solution where cloud is not accessible, or you have a limited power for access to cloud, or you have a limited latency for decision, so on sensor level decision, then immediately you met problem how using digital system achieve low latency and low power. Low power, I mean microwatt level power consumption, not a milliwatt, microwatt level power consumption.
Yeah.
Specifically, if you use a neural net model, not algorithm. If you need simple calculation, just temperature measurement, that is not a problem. But the simplest solution, for example, microphone, smart microphone, which detect voice, no voice, is the simplest neuromorphic solution. But if you want to create neural net which can detect voice in noise environment, in high accuracy, that is not easy model. And if you use digital core for simulation of this voice activity detection, it will eat around a milliwatt power consumption, 1 milliwatt power consumption. But if your microphone is battery driven, 1 milliwatt, it's sensitive. So, in our solution, it's example. Our solution, we have a 30 microwatt, 30 microwatt. So it's 100 times less power consumption. And we use full scale neural net, well trained, verified in digital model, and then we convert this chip into chip structure. We use standard CMOS technology, and your final chip perform as your digital model. And we have a line of product, but again, finally, what we open opportunity to use on sensor level raw data processing in environment and product where before nobody can use neural net. For example, in smart tires, inside the tire, where your battery lifetime must be 5 years. So, and no digital system can work 5 years always on, and you can't use cloud because, again, how you transfer data from your tire to cloud. Many industrial application, voice command system, that is area where we open new opportunities. So you can use very complicated full-scale neural net converted to ultra low power structure, low latency. Typical inference time for our core is 5 microseconds. Again, it's very fast, so no latency for data processing. So that is what we open. We work in few product line today, and every month we met new potential customer who find new interesting application where they can use this core for some, for example, gesture controls. We just few months ago met company, they have a perfectly working digital neural model for gesture recognition. But power consumption eat everything, and they just can't implement in real product. So we offer solve the problem, so you can have gesture control on your smartwatches or your wristband for long battery life without cloud connection, without latency. That is important.
Yes. Yes.
So that is generally what we provide, new opportunity.
Absolutely. So I understand that now. So I understand why you answered the question of you're not replacing something. Actually, you are, but you're just with a different approach. So I understand why you answered the question the way that you did. So what we're looking at here is, if you like, very discrete actions. So you used hand gesture or tire pressure. So what you're describing is does your system come into its own when you absolutely know what your system is looking for from the sensor side? So, and that's why, so be it a tire pressure or be it a hand gesture, whatever that is, you know, you can clearly identify that. So your neuromorphic system has already learned that. It already knows what it's looking for. It understands what it's looking for. And therefore, that's where you keep your very low power and your very low latency at its best. So, is the ideal application for you in those very discrete places where you know what outcome you are looking for? There's no chaos. This is what I'm looking for. When I see it, that's when I take an action. So I'm only using power and I'm only using latency when I need. And that's why you keep it extremely efficient. Is that the ideal solution for your technology and your chip?
Generally, yes, you are right, but it's slightly broader. So yes, we
Okay.
application specific. You're absolutely right. We application specific product,
Yeah.
uh, and we all our product is fit to sensor. It's a sensor specific. For example, for smart tire, we use accelerometer data,
Yeah.
vibration data, to detect friction coefficients, road condition. So it's
Yeah.
like you can touch the surfaces. So that is. So we take accelerometer data, raw data. Accelerometer is inside the tire, and
Yeah.
we extract friction coefficient. Yes, we did this learning, so ML learning before our chip. It's
Yes.
not self-learning. The all
Yeah.
learning
I
process is
understand.
done before, and we dedicate our core to extract exactly that information. It means friction coefficient from accelerometer. That is
Yes.
specific, but we can calibrate our core. We have some flexibility. For example, if you use new tire with new tread and we can calibrate. It's an easy process and uh, adjust this for specific tire. But it's always fitted to accelerometer and specific information. So we extract friction coefficient from this vibration. Uh, Second chip, for
So can I just
example,
ask a
yeah,
may I just ask a question on that?
yeah,
So
yeah,
I understand the low latency. I understand the low power. You've done the machine learning beforehand. That your chip sitting there knowing exactly what it's looking for. You called it sensor driven. Did you call it sensor driven? But sensor anyway. It's reliant on the data that's coming from the sensor, and you've calibrated it to understand when that sensor. Explain to me how that works when everything is in the field, because you decide, for instance, the tire changes or the conditions change. Do you do that virtually via connection to the cloud at some point to do the recalibration, or does that happen in some other way? How do you take account of the changing conditions once your chip is implemented in its embedded environment?
yeah. But that is how looks this sensor node. That is what inside the tire. It's implemented inside the tire, and
Yes.
this sensor it's integrated when tire manufacturing. That is tire vendors integrate this sensor, and when you
Right.
buy tire, it's already calibrated. So that is
Oh,
not
I
a
see.
custom.
Sorry, misunderstood. I understand now. It's done at the point of the sensor.
Yes,
So yes, I understand. So you change the sensor rather than the chip.
yeah,
Got you. That was a
yeah.
misunderstanding of mine. Okay,
And
good.
and
Right. Okay.
for example, if you are Pirelli tire producer, you have your own library, proprietary library calibration for
Yes.
Pirelli tires. If you
Yes.
Goodyear, for example, you have another proprietary. So that is on his side.
Yes.
We provide generic sensor node, and they
Yes.
did calibration on his side and manufacturing side. And when you buy tire or you buy a new car with these smart tires, it's already done.
Yes.
So you don't need
Yes.
to upgrade it.
Sorry, that's because we live in this world of the connected, embedded edge AI. We live in the world of stuff coming
Yeah,
down.
but
That's
it's
that's something.
generate complexity for customer. It's generate
Yes,
complexity.
absolutely. No, no, exactly. I now under the this is unraveling for me as in front of my very eyes. I'm beginning to understand the nuance between taking the data from the sensor, which is why you called it sensor driven, because it's the sensor you've already set the parameters with the chip, and it's the sensor that changes rather than the chip sensor getting its data, because you've done it the other way around. I understand. Okay, good. Right, we're getting somewhere. Right, so now I understand how you've created this because you've come out of the digital world. You said the digital world's very, very complex, uses and is very established, and is technologically very sound and very worthwhile. I think we all agree on that. So then you said, hang on a minute. If we have a situation where we can absolutely get a finite outcome from our sensor-driven world, we know we can train the model, we can train the chip to specifically understand the data that's coming from it. So it's sensor-driven, which was your description. So today, I've listened to this and watched this video. I've listened to Alexander. I now understand why if I was in the digital world, I can come down into the PolyN world. I then understand how it's driven by my sensor. How do I engage with you to go on the journey? You used tires, and I think you had some. Could you just give me another 2 or 3 examples of applications that you've been successful in? So tire pressuring, monitoring. Could you just give me another 2 or 3 so we can give the watchers just a scope of where you found success?
Yeah, this is first is upgrade of standard TPM tire pressure monitoring system to smart tire. We also have a lot of voice processing application.
Sorry, you did mention voice.
Yes, it's starting from a very generic voice activity detection, smart microphone. That is our first product chip, which is now today in production, and we expect available May, June for silicon verification. It's a voice activity detection, voice, no voice, with very low latency in any environment, noisy environment, etc. The second add-on to this, it's a speaker recognition. The second version will recognize not only voice, no voice, but the who I'm speaking, the owner's voice. That is important, for example, for walkie-talkie, for two-way radio, for you have a voice activation system for many applications for waiters, construction workers, police, whatever. And your radio detect only your voice. Nobody can use it, so it's like a fingerprint. So your voice, and it's radio activated by owners. It's the next one, speaker recognition. Third version, we integrate also command detection. You have voice detection, speaker recognition, and wake up word and set of approximately 20-25 command for remote control. Again, that is important. Keep in mind, so all of these work completely offline, no internet connection, microwatt level power consumption. You can integrate this for remote control, for example, for TV remote control, air conditioner remote control, and you keep this in your desk, and you can easily say TV on, air condition on, off, next channel, channel number. So the simple command, but that is 80% what we use in real life. That is a third version, and here we have a high demand from a big customer, remote control for TVs, for home appliance, air condition system. Next version here, it's for hearing support. It's a voice activity detection and voice extraction. That is not denoising. We have a lot of active noise cancellation system. It's available wide. But active noise cancellation, it's cancel noise. But imagine if you use earphones with noise cancellation and you walk by street, you feel uncomfortable because you are not listening what around you. For many people, they need reverse process. They want to hear noise if something around you. But if somebody starts
Cars, for instance, that would be handy, wouldn't it?
Yes, cars. And but you walk and you come into the shop and you start talking with cashier, and you want to listen only voice, only human voice. So that is what we provide: voice extraction. So neural net,
Yep.
when it detect voice, they extract only voice, and you not hear noise. When you finish your conversation, walk away to the street. You listen everything. You listen cars and everything around you. So that is very important. Again, why we are not a pioneer of voice extraction. That neural net is available on the market, but all these
Yep.
features today available only by cloud, because
Yes.
so you need to send voice to third party, denoising, and so it's a latency and power. So that it's no solution which is offline available in your earbuds. So that is
Yep.
our next pioneering system. So that is
Okay.
our voice. That is our voice product pipeline. And I mentioned before gesture control. So again, mm, today it's a lot of attempt to create gesture control. It's specifically important for robotic industry, for
Yep.
new Android robot control. And again, problem is the latency. If you put your wristband to you and send information from your hand to the cloud, it's too high latency.
Time.
So it's time.
Time.
So
Yep.
we can solve this problem. So it's we partner here. So it's we build cheap, but our partner, they already spent 20 years to collect data and build this very, very impressive model. And we did conversion to cheap and then provide this as low power, low latency solution. So that is current pipeline. We have few proprietary project. Customer come to us with his problem, but it's still proprietary. We can't disclose, but market is growing, and more company understand that that solution may help in few segments. But again, we are not about replacing the digital. The digital system works.
You've been very clear about that. Okay, so let's just move on to. So I think I could summarize and say the areas where you're targeting is very typical generative AI applications, where the outcome that you want is very discrete, predetermined via machine learning, sits inside. It's sensor driven, so when it's set by the sensor wherever it is. So you've described generative AI, so it's gesture, voice, sound,
vibration,
and motion, vibration. So that's excellent. So I've listened to this video. I'm a design engineer. We're not replacing. You've been very clear about that. We're not replacing. So let's not. But I go, I think that might be me. How do I go about what's my journey to engaging with you to get evaluation to find out whether this could work for me? What's the journey there?
Yeah, first of all, we always build digital MVP, so like a digital twin. Typically, we did this free or for very, very low cost. So we take neural net, which solve your specific problem, and we pass this model through our compiler system. And
so neural net is your proprietary beginning point to take in the data and start doing the machine learning. That's your proprietary start.
Yeah, the starting point, it's a neural net model. Maybe it's not a final version, it's like feasibility, but for beginning, we need a model. We have a lot of ML scientists working with us as an ecosystem, and they help us to, if, for example, you are engineer, you have a problem, you want to remove some dirty work from your digital system, and you want to do some data processing on sensor level, but maybe you don't know how to solve this. We can help, we can connect with proper expert who do machine learning in specific area. That is not our business, so we are not model developer, but we cooperate with huge ecosystem of model developers, and we integrate this. And first feasibility step, typically, again, that is not complicated to verify, is it fly or not? So we have neural net prototype, we pass this model through our compiler, and we can give you estimation of future core size, latency, and power.
Right.
In beginning,
So you sort of go through a filter process that starts with your neural net, and then you work down, and then you can work out what the latency and the power would be in the core, taking the data from the beginning, going through your proprietary process, so you're able to give an outcome of what you expect the latency and the power to be once you
yes.
embed into the chip itself.
Yes, and that platform, it's well developed. We verify it many times, and it's a plus minus a 5% accuracy on very early stage. So before you invest time in full product level development, you can understand what is the estimation. So is it viable or not? And then next step, if it's okay, if it's viable, then again, still in digital framework. Second step, it's a product model development. So you, together with ML expert, you train neural net for specific data, what you needed,
Yep.
so your sensor, to achieve accuracy or tolerance or what the result you need to extract voice or detect some specific vibration pattern and whatever. And that is in digital environment. You can use Amazon Cloud. Today, all this ecosystem very well performed and not costly. Of course, it's some expenses, but it's not sensitive. And next step, you have a digital twin. We built a full-scale digital twin. It's something like that box, for example, which have here it's a digital twin of smart voice control. Here it's a microphone, and on output you have a interface for command detection. And in that stage, you can do fully functional test. So you can play with all environment where you use it and test how it works. Everything works according spec, except power and latency, because we still digital system. So it's, of course, it's much more power, higher latency, but from functional side, it works absolutely equal. So you can detect all command, you can test if it's accuracy or some mistake out there. That is the second step. Of course, that second step it's involved more resources, but anyway, it's not critical resources because we are not in cheap design process. It's still not expensive. When everything done, digital twin is accepted, then we can go to generate real CMOS core, real chip. That is next step, and that is of course requires the quantity, because no reason did this if you need, I don't know, 1,000 pieces. So that is too expensive. But if you build a mass product like remote controls, millions of remote controls, it's no problem. We use standard CMOS process, 5540 nanometer level, so it's not very expensive. It's not high end, not like a 7 nanometer where you need millions and millions just for beginning. And we order chip which is equal to digital twin. So finally you have a small chip, microwatt power, which is equal to your digital prototype what you tested before. So that is how process goes. We cooperate with few fabs here. First chip now we produce in Skywater. It's a 90 nanometer process. And then we going to 55 and 40 nanometers to other fab. It's Taiwan and Japan-based foundry. Uh, for us, optimal node is between 40 and 55 nanometer because it's analog structure. We use analog neurons. And if we go down to 28, 22 nanometers and below, we just pay higher price for nothing because our size are not shrinking. It's not like a digital system where you, and so we stay, that is sweet spot for us, 40, 55 nanometer. And that is very mature process. And finally, we can provide very cost efficient pricing because process is not expensive. That is how it works. So
Very good.
first two steps, it's in a digital environment, and then when everything works, we do compilation. And again, we are not ASIC company. Our system is fully automated. It means we are not design new chip every time. So we have, it's like a puzzle system.
Very good, very good. Well, I think you've given us an excellent introduction to PolyN, and we've discovered the natural fact where we started thinking that this was alien technology. It's not. It's not. It's an incredibly well thought through, logical. Although you've changed it around to being sensor driven, so that already the learning's already done on the chip and it's not going to the channel, and then you're offering immense low latency and low power. This has been an absolutely fantastic introduction to your technology. Thank you very much, Alexander. Very, very good.
Yes, thank you. I'm happy to explain, and I hope the engineers who may be looking for this podcast think about new opportunities. Again, that is new opportunities in some new product where you need microwatt power and you can't find it today on the market. You can ask this, and like again,
you have a solution.
Yes, the same again as with smart tires. The industry think about this idea past decade, more than 10 years, and no solution was available to work inside the tire because inside the tire you no access to cloud, no data transfer. You must process accelerometer data inside. That is what we bring.
Very good. Thank you. Thank you.
Thank you.